So in this video, we'll talk about perpendicular lines and how this fact of the lines being perpendicular to each other manifests in terms of their slopes. Right, so the first thing to understand is what do you mean by perpendicular lines? Well, as the name suggests, from its Greek or Latin origins, or wherever it comes from, two lines are said to be perpendicular if they intersect at 90 degrees. That means if this is one of the lines, L2, and this is the other line, L1, they must intersect at 90 degrees to call them perpendicular to each other. So this is a relative word that we use, relative to each other. And if that is the case, then all the angles, if you work them out, should be 90 to each other. And by that I mean that this angle should be 90, so must this angle be, and so must this angle be. Right. So let us consider that this line has the slope m sub 1 and this line has the slope m sub 2. From our previous videos, it would be clear now that if a line has a slope m, it makes an angle theta with respect to the positive x-axis, then tangent of theta turns out to be m. That is how we define our gradient or slope, or a value which is a measure of the steepness of the line, right? So that is how we define theta as with respect to m. So similarly, using that concept here, say line L1 makes an angle of theta 1 with respect to the positive x-axis. That means this angle be theta 1. And say L2 makes an angle of theta 2 with respect to the positive x-axis. So we're always measuring the angles in this direction. We're always going from the x and going towards the line. Always going from the positive x, going towards the line, always in that fashion. So these two angles are known, and they are theta 1 and theta 2. And if we know the slopes of the line, then we know theta 1 and theta 2. So we can write the same relations here. Tangent of theta 1 should be equal to the slope of the line that it corresponds with, and tangent of theta 2 should be the slope of the line that it corresponds with. And we have also chosen to draw the lines in a perpendicular fashion, thereby this angle being 90 as well. So now that we have all the angles known in this triangle, this right angle triangle, we can relate theta 2 to theta 1. And we do so by using the exterior angle property. Since this theta 2 turns out to be the exterior angle of this triangle, therefore theta 2 should be equal to theta 1 plus 90 degrees, the sum of the two opposite angles to the exterior angle. The other way to look at this is the angle sum property of triangles, which is 180. That means that the sum of all the interior angles is 180 for a triangle, and that should be theta 1, this angle, plus 90, this angle, plus this angle, which is 180 minus theta 2. You can add them up, cancel 180 degrees from either side, and shift theta 2 to the LHS to get theta 2 equals 90 plus theta 1. So simple as that. We just use the exterior angle property of a triangle, and we got this form. Now we have related theta 2 to theta 1. This is the relation for the two lines, M1 and L1 and L2. We can do now is we can take the tangent both the sides. Therefore, tangent of theta 2 would be equal to tangent of theta 1 plus 90 degrees. If you work this out, tangent of theta 2 turns out to be minus tangent of theta 1 inverse. There is a very clever way to look at this. If you forget the relations of tangent some angle plus 90 degrees, what is the form of that? We can always convert it in the form of sine and cosine. So as we know that tangent of theta equals sine of theta divided by cosine of theta, therefore tangent of theta 1 plus 90 degrees turns out to be sine of theta 1 plus 90 degrees divided by cosine of theta 1 plus 90 degrees. You can work that out, you can expand the two formulae in terms of cosine and sine, and you will see that sine of theta 1 plus 90 turns out to be minus cosine of theta 1, and cosine 90 plus theta 1 turns out to be sine theta 1. So this becomes negative tan theta 1 inverse, or we also call this to be negative cotangent of theta 1, or cot theta 1. So using those formulae, we can write tangent of a angle plus 90 degrees and express that in this form. Now, using the initial relation that related the tangent of theta 1 and tangent of theta 2 to the slopes, we can use both of them to express this equation in terms of m1 and m2. So tangent of theta 2 turns out to be m2, simple as that, and minus 1 upon tangent of theta 2 turns out to be theta 1 turns out to be m1. Therefore, we can multiply both the sides by m1 to get m1, m2 turns out to be negative 1. Therefore, if two lines intersect at 90 degrees, the slopes should multiply to give you the value of minus 1. This is the property of perpendicular lines in a Cartesian plane, in a rectilinear coordinate system. And we can do an example here by choosing particular values of the slopes. So let me just erase that, all that, and here we go. So let the first line L1 be of the form y equals 2 by 3 x plus 7, say, right? This is our first line. We want L2 to be perpendicular to line L1. So the slope of L2 must be such that the product of that multiplied by the slope of line L1 be negative 1. So if the slope of L2 is m1, say, then m1 times the slope of L1, which is m1 times, if you see that this is of the form y equals mx plus c, where the coefficient of x gives you the value of the slope of the line, we can use that fact to substitute for the slope of line L1 as 2 by 3, and that should be negative 1 by the property of two lines being perpendicular. Therefore, we can simplify this to get m1 equals minus 3 by 2. Therefore, our line must be, L2 must be of the form y equals minus 3 by 2 multiplied by x plus some intercept that we have not yet established. Now, it may seem odd to represent a line in the form of this, where we do not substitute anything for L1, which should be the case because the only condition that we want on line L2 to be such that it is perpendicular to line L1. If you have this as line L1, then you can have this line as L2, which is perpendicular to it. You can also have this line, which is perpendicular to it. Or you can also have this line, which is perpendicular to it. If you notice, all of them have a different intercept value. For example, for this line as L2 has this intercept value as C. And for this line, the intercept is much smaller. This could be some other value of C. Therefore, we just leave it in terms of C. We can substitute for C given any other condition that the line L2 passes through a particular point, and so on and so forth. So we can really reduce the possibilities of infinite number of lines, which turns out to be perpendicular to a given line, to a particular line. And that is how we would work this out. But the important point here is to remind yourself that if two lines are perpendicular to each other, then the slopes multiply in this fashion, that m1, m2 turns out to be negative 1.